in the morning today, and the afternoon is left free for you to have some informal discussions or alternatively explore Cambridge. Depends what you want to do. Could I just remind everybody that the talks are broadcast live to the world and also recorded, provided the speaker signs the form, which I encourage them all to do. But because of the broadcast, please, if you have a mobile phone in the auditorium here, could you switch it off? Because apparently it interferes with the signals going out there, and people who are watching somewhere else in the world will keep hearing these irritating beeps and so on. So it's a pleasure to introduce our first speaker today, Chuck Gartland from Kent State, and I'll hand over immediately to him. Over to you, Chuck.
Thanks, Mark. I'm grateful to the Institute, to the organizers of this program, and to the organizers of this workshop for the opportunity to talk about this. What I'm going to talk about is kind of grew out of some numerical modeling experiences that I've had over the years, working on different projects, modeling at typical scales of devices and experiments, equilibrium orientational properties of director fields and such with coupled electric fields in the framework of Oseen-Frank elasticity, so kind of the standard old-fashioned type of modeling. The types of numerical investigations that I've had to do on a number of occasions involve numerical bifurcation and phase analysis. We always want to construct some kind of a phase diagram for these systems, see how things change with the parameters. The way I typically approach it is I start with just a direct discretization of the free energy. So F here will come from either some kind of a finite difference or finite element approximation to a free energy, which is an integral functional of the director field and some electric potential. And so then this N contains all the degrees of freedom associated with the director variables, and the phi contains all the degrees of freedom associated with the electric potential on every grid point or mesh point, or however you happen to discretize your system. And then at each point where there's a director degree of freedom, Lagrange multiplier is introduced to enforce the unit length constraint. And so the equilibrium equations can be formally put in the setting of critical points or stationary points of a Lagrangian function. And then I want to follow paths of equilibria via parameter continuation, detect bifurcation points, switch onto bifurcating branches, assess the local stability of the solutions, compute their free energy, compare the free energies where there is coexistence, and just chart out a good phase diagram that contains all of the information. So I don't want to go through the details, but this is kind of the generic sort of thing that you have, where somehow you have indicated multiple equilibrium solutions existing for a certain range of some control parameter. Some branches are locally stable. Some branches, the heavier branches would be the globally stable branches where there's a first order transition, and that's determined by finding where the free energies cross over. And then you watch how these things change. You collect all this information, and you put together a good phase diagram. So in the course of doing these kinds of numerical investigations, if you're forced to use this kind of a framework, where you're forced to work with the director components, you can't introduce orientation angles. And so you have these Lagrange multipliers. The system is it's highly indefinite. The Lagrange multipliers make it so, and also the coupling to the electric field makes it so. So it's not even completely obvious numerically how to assess the local stability of an equilibrium solution. It's not hard once you think it through, but it's not as easy as in kind of a typical situation where you simply compute a minimum eigenvalue of a Hessian. So it was in sorting that, kind of worrying about things like that led me to what I'm going to talk about today. So I'm going to talk about today sort of the extension of kind of the numerical side of this to more of a continuum setting, the effect that the coupling between the liquid crystal director and the electric field can have on electric field induced instabilities, such as typical Frederick's transitions. and the anomalous behavior of one particular Frederick's transition, the electric field induced Frederick's transition, which seems to behave in a little bit funny way when you carefully look at the effect of this coupling. So the type of free energy I'll look at is has a certain generic form. I don't want to get into the details with all the material constants and things, but I'm equilibrium setting. I'm imagining it is essentially a capacitor held at constant voltage with a liquid crystal dielectric, the kind of the typical situation in devices and such. The electric field is given as the negative gradient of an electric potential. The free energy involves both the director field N and the electrostatic potential. The total combined free energy I call a W. There might be some weak anchoring condition on all or part of the boundary, which I allow for just for some generality. And now the free energy density here has a distortional part, kind of a typical Oseen-Frank part, and then the piece related to the coupling to the electric field. The distortional elasticity is just Oseen-Frank. The simplest thing you can think of would be an equal constant version of that model, which is adequate for what I'm just worrying about here. N is the director field, forced to be a unit length throughout the entire region. And then the electrostatic energy is 1/2 the displacement vector dotted with E. In this regime, this is just some dielectric tensor that depends upon N times the grad of the electric potential, dotted with the grad of the electric potential. The system is that of a uniaxial, the medium is that of a uniaxial crystal, so the dielectric tensor in its eigenframe has one distinguished eigenvalue, epsilon parallel, and a degenerate pair. In a tensorial notation, it's most conveniently written in this way. The dielectric anisotropy is the difference between the susceptibility parallel to N versus perpendicular to N. Surface anchoring could be a typical Rapini-Papauer kind of thing. And so I could have, in fact, Dirichlet boundary conditions on part of the boundary, weak anchoring conditions on another part. It really doesn't change much. I just allowed for that generality to show how it affects some of the boundary conditions and things. So the general form of the free energy then is some distortional elasticity, the electric field coupling, which looks like this, possibly a surface anchoring potential. And then the prototype is just the equal-elastic constant model. If I kind of flesh out the electrostatic term this way, it's frequently done just to enable a simple interpretation of the influence of the coupling of the electric field to the director. If epsilon A is positive here, by virtue of the negative sign that is in front of this, then the minimizing this with respect to the director field encourages N to align parallel to the electric field. If epsilon A is negative, the reverse is true. It encourages N to align perpendicular. Both situations arise in practice, but this is pretty familiar background, I think. The boundary conditions that I'll imagine then is I imagine I have Dirichlet boundary conditions on part of the boundary, gamma naught. There'll be some natural boundary conditions that arise from the anchoring potential on the other part, the complementary part of the boundary, gamma 1. For convenience, I just assume I know the electric's potential on the complete surrounding boundary of the cell. There are a variety of other things that can happen with the electric potential. The electric field could extend beyond the cell, et cetera, but this is just for the simplicity. The equilibrium solutions characterized in this setting can be characterized various ways, weak and strong forms. At the end of the day, you're trying to minimize the free energy with respect to the director field. However, the electric field enters in kind of a funny way. So, yeah, if I let this N sub B denote admissible director fields, so these would satisfy the boundary conditions, be sufficiently regular, and satisfy the pointwise unit vector constraint that's sort of described here in more detail. The admissible fields for the electric potential required to satisfy the Dirichlet boundary condition that it must satisfy. I'm not getting into the details of the regularity conditions. The globally stable phase then, by virtue of the negative definite way that the electric field enters here, is a sort of a minimax problem. It's minimizing. Oops, sorry, I hit the wrong button. It's minimizing with respect to the director variables, but it's actually maximizing with respect to the phi variables, because epsilon is a positive definite tensor. So equivalently, you can look at it as a minimizing free energy, which with subject to a side constraint that sort of the electric field satisfies the appropriate electrostatic, or the electric potential satisfies the appropriate electrostatic condition. But it's this minimax aspect of that gives a little bit of a headache to some things, at least at the numerical level. So I guess one point is that there has sort of an intrinsic minimax nature, or you can think of it as a PDE side constraint minimization of the liquid crystal director. Now the first order conditions for the equilibrium that can be written in various ways, and I'm going to need to put some of this stuff, most of this stuff, in sort of a weaker variational form down the road, but here I'll have it kind of laid out in both ways. In some sense, if you just do the formal first order necessary conditions that arrive from the constrained variations, you arrive at the conclusion that the first order variation with respect of the free energy with respect to the director variables must vanish on all admissible test fields, or all admissible variations, which must vanish on the Dirichlet portion of the boundary, and they must be transverse to the director field n naught. So this is essentially the tangent space to the constraint manifold NB that I had before. The electrostatic equation can be viewed as just the first variation, comes from the first variation of that free energy with respect to the electric potential, and its tangent space is essentially just fields that must vanish on the Dirichlet portion of the boundary, which we're taking to be the whole boundary for the electric potential. Now the Lagrange multiplier version of the formulation is needed, at least the way I've got it sorted out for to do the stability characterization. So an alternate version of this would be to free up your variations and introduce appropriate Lagrange multipliers. So these fields no longer have to be in this sort of tangent space with respect to the pointwise constraint. They're free, but they do have to be vanished on the Dirichlet portions of the boundary. And then the Lagrange multiplier rule, or Lagrange multiplier version of this, of this first order condition becomes this condition. First variation must be counterbalanced by a Lagrange multiplier in the bulk and a Lagrange multiplier on the free part of the boundary. And then the electrostatic equation, this is the same equation as here, just written out in its weak form instead of its differential form. In strong form, it's just a familiar coupled PDE system. In the simplest case of an equal constant model, you would just have a Laplacian of the director field over here. In the more general case, it's supposed to be W. That's the distortional part of the free energy density. Lagrange multiplier, the coupling term to the electric field. This is sort of the equilibrium equation for n. N has to satisfy a prescribed strong anchoring condition on the Dirichlet portion of the boundary. The natural boundary condition that comes up on the free part of the boundary reads as follows. There's a Lagrange multiplier that is introduced in the boundary condition, and then the strong form of the electrostatic problem can be written in that form. It must agree with its specified Dirichlet boundary conditions. So the question then is, if you keep everything in this coupled way and approach things in this way, how do you characterize the local stability of an equilibrium solution, since you have indefiniteness because of the Lagrange multipliers as well as the electric field? And so from the intuitive or from the physical point of view, I think the bottom line is that the director field has to minimize the free energy, and the electric field is in essence just slaved to the director field by the electrostatic equations that define it. So if you adopt that point of view and want to use that to derive some version of a stability criterion, it leads you to sort of forming what I refer to as a deflated free energy, where I take my full free energy involving the coupled variables n and phi, and I remove the phi variable. You can either think of that as by doing the inner maximization in the minimax problem, or for some calculus I'm going to do in a moment, it's convenient to introduce sort of an operator that I call T that simply takes a given director field and returns to you the electric potential associated with that director field. So you just try to solve the PDE side condition for the electric field that goes with that particular director field. That's a well-posed problem, unique solution for any director field that you put in. And then here is a characterization of that T operator in its weak form. This is just the solution that comes out of this is just the solution of the electrostatics problem in weak form. It simply looks like this. If there are no free charges or no spontaneous polarization or flexoelectric polarizations or anything, it has to satisfy the boundary conditions. This must be valid for all test fields vanishing on the boundary. Now this is a very nice problem. The epsilon tensor is a real symmetric positive definite tensor. No matter what director field you put in there, its eigenvalues are bounded between a lower bound here and an upper bound here, involving the free space constant epsilon naught and the relative dielectric constants epsilon parallel and epsilon perp, both of which are positive. And so this is a nice problem that underlies this T operator, and it's fine and easy to work with. The other thing that I need to do is, if I'm going to look at the changes in the electric field that accompany changes in the director field to assess stability, I need essentially the derivative of this T operator. It's a global derivative, Frechet derivative. So I denote it as dt. And so for a given equilibrium director field n naught, dt will take some small variation or some small perturbation of n naught and return the accompanying small variation in the electric potential that would come from that at first order. And so you just linearize the equations, and you can characterize this derivative in either strong or weak form. In weak form, it winds up looking like this. It looks the perturbation psi satisfies I'll write this in strong form in a moment, an electrostatic sort of problem. And then there's sort of a polarization that arises in the linearization that acts as a source term on that problem. And this is sort of the key coupling term for some of the effects I'm going to talk about. So there's this thing that I denote as little d naught. It's actually a linear function of the perturbation v here. And it's just what you get if you go into the electrostatic problem and linearize around a given director n naught, perturbing it to n naught plus v. So this is what it is, where E naught is the electric field associated with sort of your ground state electric potential, and your ground state electric potential is the electric potential associated with your equilibrium director field. Now the simple interpretation of this quantity is it's essentially the first order change in the electric displacement associated with a perturbation of the director field. Now, there are other ways you can see this arising. Like you can get it out of the strong form of the electrostatic equation just by doing a linearization. There are various ways you can see it arising. Here's another way you can see how this d naught comes out. If you calculate the second variation of your free energy, regarded the original free energy, not the deflated one, regarded as a function of both n and phi, you break your second variation into these three sort of separated parts. This term that I referred to on the previous slide in the red box as d naught arises through the mixed terms, the terms that involve the coupling between N and phi. Now, once you've passed to this sort of deflated free energy, you've factored out the electric potential, you're left with this reduced potential or this deflated potential F tilde. It is coercive, so it has global minimizers, and so your solution, your globally stable phase, is kind of well characterized in terms of this thing. There's no funny business, no indefiniteness to worry about here. And so this is the whole reason you might want to switch to this point of view. So this thing has a minimizer, and you can characterize your globally stable phase of your solution system as simply the director field that obeys the boundary conditions, obeys the unit vector constraints, and minimizes F tilde over all possible such values. Now, once you find that, you can easily append to it the appropriate electric potential that goes with it from your T operator, and you find that the appropriate characterization of your pair, equilibrium pair, as the globally stable pair will be the globally stable the equilibrium pair that delivers the least free energy. So in situations where there's multiple coexisting equilibria, you just calculate the free energy of all of them, compare them head to head. The lowest free energy wins. And by virtue of the one-to-one mapping back and forth here, it just simply corresponds to the global minimum of the deflated free energy. Now, in terms of the deflated free energy, the first and second order conditions are less complicated. In the Lagrange multiplier version, it's simply the first order condition that's necessary for equilibrium is simply this. Again, it's the same Lagrange multiplier in the bulk, same Lagrange multiplier on the boundary. The second order condition is essentially that the second variation of the Lagrangian is positive definite on the tangent space. So basically, it comes down to something like this. You need the Lagrange multipliers from your equilibrium condition, and then these are the constrained variations that are everywhere transverse to the local equilibrium director field. But this now is something that I can work with. I can accept this as kind of the natural characterization of local stability. I just need to now put it back into the language of the undeflated free energy. And so there's just a little bit of calculus that one has to do to go back and forth between the first and second variations of the deflated free energy and the first and second variations of the original free energy that had both N and phi in it. I'm doing okay on time. So it's just you have to use some conditions along the way to simplify this. The first variation involves both the first variation with respect to the director variables and a first variation with respect to the electric static variables, and then sort of a chain rule term that introduces the derivative of your mapping here that maps you from director fields to electric potentials. But by the definition of this mapping, it is precisely such that this electric field, this electric potential satisfies the equilibrium electrostatic equation. So the second piece goes away, and you're just left with this. So the first variation is rather simple. The second variation is a little more complicated. You get second variation with respect to N. You get a second variation involving the N phi coupling. There is again a chain rule term that introduces a derivative of your mapping T, and now you have to use sort of two other facts to kind of simplify this expression. Which this arose. This is where sort of the definition of D naught came from. This is basically the equation that characterizes the psi going from V to psi. The D naught is linear in the V. And then then this allows you to simplify the right-hand side here and get it, this form is actually useful and convenient here. So at the end of the day, once the calculus is followed through, the second variation of the deflated function involves the second variation of the original free energy with respect to just the director variables. But then there's an additive piece that is in fact a positive definite quadratic form in the psi variation, which is sort of slaved to the v variation through the derivative of the t map. I'm sorry, this is a little, I've struggled to try to put this in digestible form, and as I'm going through this, it doesn't seem too digestible. But anyway, but at the end of the day, if I take my my stability characterization, my sort of second order conditions expressed in terms of the deflated functional, and now I put it back in the language of the original functional, the main difference is this term that's been highlighted in red has been introduced. So what this is saying is that an equilibrium pair, N naught, phi naught, a director field and an electric potential field that satisfy the equilibrium conditions, the coupled equilibrium conditions, it will be locally stable. Well, this is sort of the first order necessary condition. If it is locally stable, then necessarily this quadratic form must be bigger than or equal to 0 for a certain class of admissible variations. Now, it involves the second variation with respect to the director variables of the original free energy. It involves this extra positive definite piece that was introduced through the going back and forth between the deflated formulation of the problem. It involves the exact same Lagrange multipliers on the boundary and in the interior that were in the corresponding statement for the deflated problem. And here the only sort of funny business is that this should be a quadratic form in sort of pairs, u variations of n naught and some variations of phi naught, but the variations of phi naught are in some sense slaved to the variations of u naught through the derivative map. So it is sort of an eigenvalue problem in disguise. It's just that there's a bit going on with the interplay between the perturbations. And again, the u's have to be in the tangent space. The u's have to be the transverse u's vanishing on the boundary. You can write this in different ways. I haven't been able to come up yet with a good way to write it in a strong form. You can, instead of introducing this derivative map, you can kind of put it behind the scenes by a maximization problem. You can look at the full second variation here, but maximize out over the size. It has the exact same effect here. These terms remain the same. So in any event, this turns out to be highly analogous to the numerical version that you get when you do some of the kind of modeling that I was referring to earlier. Now, I think the points that come out of this analysis to me were essentially the following. I mean, there's a key role played by this quantity that I call a d naught, which is essentially the perturbation in the electric potential that's induced when you perturb the director field a little bit. And now, if you look at the way the induced perturbation is related, the strong form of its equation reads like this. This is the relationship between sort of a perturbation u in the director field and the perturbation psi in the electric potential. It satisfies an electrostatic problem, but it now has something like playing the role of sort of a charge density on the right-hand side. D naught has the same units as a displacement or a polarization. So this is some kind of an effective charge density, and this is like a anisotropic Poisson equation with homogeneous boundary conditions. So here you can draw a couple of quick conclusions. If the D naught vector field is divergence free, then your right-hand side here is 0, your boundary conditions are 0, you have a homogeneous problem, and your psi solution has to be 0. So this means that this sort of extra term that kind of appears in your eigenvalue characterization, which is a positive definite term, it can only boost things upwards, it's 0. So it really has no effect at all. I mean, you have essentially the same story you would have if you kind of ignored the coupling between the two fields in terms of assessing the finding bifurcation points and things like that. So if this is divergence free, coupling has no effect on local stability of an equilibrium phase. If, however, this has a non-vanishing divergence, then this problem will have a non-vanishing psi solution, a non-constant psi solution, and this thing will be a strictly positive quantity. And what this means is that this coupling between the electric field and the director field at a bifurcation point can have an influence, and the influence can only go one way. It's only a sort of a stabilizing influence because this is a positive definite quantity. So in principle, it can only elevate an instability threshold. It can never lower it. The other kind of aspect of which is still a little funny, is that the phi naught variation psi ends up being sort of slaved to the variation in the director field in this version of things in the exact same way or analogous way to the way that the electric potential is somehow slaved to the director field. So that was kind of the main upshot of my attempts to transfer into sort of a continuum realm some stuff that I had to grapple with as a numerical analyst, doing some numerical modeling of some systems and trying to come up with a nice, clean, simple computational way of determining when a computed equilibrium pair was locally stable or not. But there are some interesting simple conclusions that you can draw from this kind of complicated looking development. And one is once I kind of figured this out, I just looked at all the standard Frederick's geometries to see if there was any kinds of couplings present where this D naught factor could come into play. Anything funny could happen with the Frederick's thresholds as a result of this. And in fact, it's very easy to come up with an example that works. So if I just take standard Frederick's transitions in the splay geometry versus the bend geometry. So I'm imagining a cell, some thickness d in this geometry. I'm imagining strong planar anchoring conditions, an electric field in the vertical direction, so-called splay-Frederick's geometry with an electric field. In this situation, I'm imagining cell, same thickness, but with a strong perpendicular anchoring condition, a homeotropic anchoring condition, and an electric field in plane, so-called bend transition. And so, as is well known, once the electric field reaches a certain critical strength, the purely horizontal director field will lose stability and tilt up and form some kind of a deformed state of lower free energy. Same thing over here. Once the electric field reaches an adequate threshold, the perfectly vertically aligned director field here will tilt into the horizontal direction a little bit. So the electric field splay Frederick's transition has been well studied. I think at least there's a nice account of it in Ian Stewart's book, and where he is adapting mostly from a paper of Doyling in 1972. I find this to be most easily digestible in terms of standard Cartesian components of these quantities. So my apologies to those who don't like components. So in the splay geometry, sorry, the left picture here, The ground state director field is in the x direction. The electric field is in the z direction. So the ground state director field is plus or minus 1, 0, 0. The ground state sort of electric field is in the z direction, some magnitude in the vertical. U is going to be sort of my perturbation that I can add to this that will preserve the constraint to first order. If I'm just constraining things to be in x, z, nothing happens in the y direction, that means that U can only have a component in the z part. And all the fields are assumed to only be functions of z. So U must be of the form of 0, 0, and some scalar w. If I look at this d naught that came out of my coupling analysis and my linearization, this was the form that it took. This was the definition of that term. Epsilon naught, epsilon a, my ground state director field, my perturbation, tensor, ground state director field, acting on the ground state electric field E naught. And now here, N naught dot E naught is 0, so this second term contributes nothing. U dot E naught gives you an E naught times a WZ, and then that goes in the N naught direction. So this D naught winds up taking this form if you just put in those representations and evaluate the quantities. And the key determinant was whether or not that was divergence free. Well, in this case, it is divergence free. The only non-zero part is here. Give away all my surprises. The only non-zero part is here, and it's a function of z. It has no x dependence, so when you take the divergence, you get 0. So there's no effect on stability. So that means that if you do the analysis carefully and properly, you just end up with sort of a critical value if you express it in terms of the electric field instead of the voltage. It ends up looking like this. In terms of your material quantities, K1 is the splay elastic constant. If I had a full Frank model, it would just be K if I had the equal constant model. And you can contrast that with what you would get out of the magnetic field version of this. And the magnetic field version of this is essentially the same. The difference in modeling the magnetic field transition is that to this order of modeling, the magnetic field is treated as completely uniform throughout the sample, and the electric field, the director field has no influence on it whatsoever. So basically, this is sort of the textbook thing. This is, in fact, if you read Dejean and Pro, they will say you want to get they'll first work out the formulas for the magnetic field Frederick's transitions. They'll say if you want to get the formulas for the electric field Frederick's transitions, just change mu naught to epsilon naught, delta chi to epsilon a, and you got it. And for this case, they're right. So treating the electric field more or less as remaining constant through that transition gives you the right answer. The bend problem is a different story. Sorry, just dance back here for the picture. The bend problem, my ground state director field is in the vertical, so that's the z direction. And my electric field is in the horizontal, in the x direction. So my perturbations that preserve the unit length constraint to first order will have to be in the x direction as well. And so my n naught is in the z direction. My perturbation is in the x direction. Everything is just a function of z, so I have some scalar u of z there. My ground state director field is in the horizontal in the x direction. It's some magnitude scalar E naught in the first component there. If I plug this into my formula for D naught, and I'm skipping the details this time around, I get a vector that looks like this. Constant, constant, constant times the u of z that used to be up here but got moved down there through the algebra of the tensor applying to the E naught. And now this thing is no longer divergence free because partial with respect to z here introduces a u prime, which in general, that will be the mode of instability that, let's see, it's going this way now, that it will not be expected to be zero. And so, and in fact, if you'd carefully do the analysis of the electric field threshold, it's different than the simple sort of magnetic field analogy. If you take the magnetic field version of this transition and just change the variables to the electric field counterparts, you would get this. But if you carefully do the coupled stability analysis, take into account the coupling between the director field and the electric field going through here, you pick up an additional multiplicative factor of epsilon parallel over epsilon perp in front. And this is something that is strictly bigger than 1 in the case of a positive dielectric anisotropy. And so you do have a strictly elevated bifurcation point, and it kind of comes out rather simply and rather easily. And so some remarks. This effect is not small. For 5 CB at some other values of whatever these things depend on. This is the epsilon parallel. Well, I mean, these NCBs have very large birefringences. So this epsilon parallel is 18.5. Epsilon perp is 7. So if I put this in here, I have to take a square root and change it to voltage. But it ends up being 63% higher if you use the material numbers for 5 CB. I mean, that's a significant increase. The other thing that doesn't come out of this analysis, but I was made aware of by Peter Palfy from some experiments that he had done with a former PhD student of his, Barbara Friskin. Not only is the transition elevated here, but the transition can be first order or second order, depending upon a simple relationship between the elastic constants and the dielectric constants. Normally all these standard Frederick's transitions are second order transitions, but in this situation, if the ratio of K1 to K3 is strictly less than 3 times epsilon A over epsilon parallel, and here's the value for 5 CB of 3 times epsilon A over epsilon parallel. So this is in some sense the typical, I mean, if K1 and K3 are normally rather comparable, this ratio should be thought of as normally not too far from 1. And all it has to do is be smaller than 1.86 in this case. So this I think for 5 CB, this is in fact expected to be a first order transition. Now, the bad news is, so I thought I wrestled with this for a long time and kind of finally figured this all out, and I thought it was really cute and a really neat story. And in fact, I mean, some of the books are flat wrong in what they say about this. Unfortunately, I wasn't the first person to realize this. So here I'm reading more carefully some of the references to some of the other experimental papers I was looking at. There was a 1984 paper by these co-authors where essentially these same 2 key features were observed, analyzing it from a different point of view, not quite the full-blown general development I've given here, but they did give, once you decipher the notation, essentially the same formulas for the elevated threshold and the changing from first order to second order transitions. So that I found very depressing, but now I'm acting as a publicist for these guys instead of whom I've never met. I don't even know if they're still alive, but at any rate, here is just an illustration of the switching from a second order to a first order from some numerical modeling that was done by a former student of mine as a master's thesis project, where we just, this was a long time ago, but it was the crossing over. I think this was a situation in which the parameters were from some experimental paper. The K1 over K3 was about 0.84, and he was just playing with the dielectric constant using some numerical bifurcation software to see you know how it went, and indeed the transition is first order in the sense I don't have all the stabilities and the free energy lines indicated here, but basically it's a subcritical bifurcation when this is larger than about 0.84. Here we're getting kind of close. Here I think is the precise crossover point where this is essentially opening to the right like a quartic instead of a parabola. And here we've gone over into the standard second order setting. Okay, so I can wrap up the my conclusions. I mean, I think for me at least, it was a rather, if you're forced to deal with this problem in this way, this coupled way, you can't use angle variables, you can't, there's no convenient way to eliminate the electric field, then this assessment of local stability is somewhat complicated by these two features, the pointwise constraint, which introduces these Lagrange multipliers, and the intrinsic minimax nature of the free energy, which is by virtue of the way the electric field enters. You can't. There are similar. I mean, you can include other things into the story. You can have a permanent macroscopic polarization. It'll couple linearly to the electric field, so it just enters in sort of an additive way, but it can, in principle, have some effect on transition thresholds, as can polarization introduced via flexoelectricity. They just produce sort of an extra, like on the right-hand side of that equation involving D naught, instead of having a div of D naught, there would be a div of D naught plus P, where P could be a ferroelectric, a permanent polarization, or a distortion-induced polarization. I'm not there. There is a numeric. I mean, in fact, the numerical version of this is what I figured out first, and then I tried to figure this out in the continuum setting. There is a way you can use exactly these same ideas, and I don't have time to explain what all of these matrices are. But if you're doing a numerical version of this, you want to get down to some kind of a setting where your calculation of your stability comes down to a minimum eigenvalue calculation. You can do that, and all of this is in essence a numerical linear algebra analog of the criterion that I walked through a few pages earlier. This Z matrix is related to sort of projecting transverse to the local director field. A is essentially the second variation of the free energy with respect to NN. C inverse is essentially my T operator. It's taking a given director field and sort of delivering a electric potential. This is kind of what comes in from the deflation of the electric field. It's called a Schur complement in the numerical linear algebra world. So some references on this. I got started on some of my thinking from this paper of Epifanio's with Ricardo Rosso and Samo Kral. Here's the paper I referred to earlier, or one of the two that Peter wrote with Barb Friskin, where the experimental evidence of both of these things appears. This is the pictures I took from this master's thesis. And then I gave this talk in Minneapolis, and Gaetano Napoli was in the audience. And he came up afterwards and he said, "Oh, by the way, we saw something similar in a paper." So this was a paper he had done with Bevilacqua. I don't know him, but where kind of something analogous, an elevation of a threshold due to an electric field coupling emerged. Okay, thank you very much.
Very much, Chuck. We have time for one or two short questions.
So in that elastic energy in which you have the competing effects, right? If you non-dimensionalize in a physically relevant context, are you gonna get like some small constants in front of phi?
Yeah, no, I think not in this case, because I mean, in essence, I mean, if everything is put in sort of the standard units, maybe.
When you have an electric induced field, right?
Right.
You'd expect that as small.
Right, but the coupling between these is quite balanced. Yeah. So here's a good one. The coupling between these is quite balanced. So if you non-dimensionalize your lengths by the width of the cell or the geometry of omega, you introduce sort of a uniform 1 over d squared from all of these grads. And then if you express everything in SI units, these guys have essentially the same ballpark magnitude. This is like of the order of 10 to the minus 11 farads per meter. This is of the order of 10 to the minus 11 joules per meter.
So they're all comparable.
They're all comparable. And in fact, I mean, for the transition to take place, they have to be kind of balanced. That's why you get the crossover. So it's not analogous to, the Landau thing where you've got something going large, something becoming quite small.
Is there quantitative agreement with the experiment for this elevated threshold?
Yeah.
3%?
There is. Now, there is in the sense that I did go through the exercise and looking carefully at the experimental data in one of Peter and Barb's papers. They were focusing on the first order versus second order aspect. But I looked at the numbers and I put them in. And in fact, this was consistent with this. I mean, in the sense that the bifurcation point that I got was to the right where they measured their first order transition, and it was and the bifurcation you would have gotten if you did not take into account the coupling was to the left of that. So the numbers are consistent, so there must have been this going on, but all that was reported in their paper was the precise transition. Although there was some coexistence. You were doing capacitance. There was like a hysteresis. Yes, but it was that was consistent. It might be nice to do some experiments to kind of more carefully pinpoint some of these things, but.
Okay, one last question from Nigel at the back.
Your Venn geometry, how do you know the perturbations are exactly as you show them, just dependent on Z and not X as well? Because you're putting a field in the X direction, presumably you've got, in a real situation, you've got some electrodes,
Yeah, no, well, that was kind of an assumption. I mean, in principle, in all these transitions, if you free things up enough, you could become unstable to some kind of a periodic distortion in one of these other directions. So, I mean, that can happen. I mean, I was just forcing it just because that's kind of that's the standard picture you expect. But I didn't do anything to guarantee that.
Okay, let's thank Chuck once again.